the best way, like I like to look at it without having to like sort of miss a cycle, is sort of you can do like two separate ways. You could count, you could literally just look at the graph and count them yourself, because sometimes matrix multiplication actually doesn't give you the right number of cycles because you might be double counting certain cycles, which we can look through when we look at sample problems, right? So so you can represent a graph with a matrix, and so basically the matrix we make from just, filling out the adjacencies will give us all possible paths of length 1, right? So if we were to multiply this matrix by itself over and over again, we'll get matrices which represent the number of paths that will represent the paths of length 2 or 3. And this is by just, multiplying the adjacency matrix by itself over and over and again. So if we go to the next slide, so this is our first problem, is finding the different cycles contained in this directed graph below. So one of the ways we can look at it is just starting, we can obviously just start from with each different vertex, right? So if we start from vertex A over here, we know that we can go, wait, let me get a pointer up. So if we start from vertex A over here, and we go, so the only place vertex A can move to is vertex B, right? And then vertex B can go back to A. So that's one cycle right there. A, so if you were to write it out, which I'm going to try to do with this pencil, you have A, B, A. So that'd be one of our cycles here, A, B, A. You're starting from A, and you're going to B, and you're coming back to A. So that's one possible cycle here. Now, if we were to, so obviously the only place A can go is B, so A can go to B. Now B can go to, the only place B can go to is C, right? Now, how are we supposed to, so now we're gonna have to figure out a way to redirect back to A. And so if we were, so let's say we were go to A, we start at A, and we go to B, and then we go to C, obviously, because that's the only one available, right? And then the only one available from C to go to is D. Oh my God. And then D can go to E, and D can go to B. Another thing about cycles is you don't want to repeat letters in the path when you're going to A. So for example, if we were go to A, B, C, D, and then we went back to C, that wouldn't count as a cycle, because the cycle needs to have only, other than the start and end node, there shouldn't be duplicate vertices within the path, right? So you go to A, you go to B, you go to C, you go to D. If you go to E, it's a dead end. You won't be able to get to A, so you don't go to E. If you go back to C, the only way, it wouldn't count as a cycle. So the only way we could go is back to B, which we can't do obviously because A, B, C, D, and then we have another B. So the only cycle, if we were to start from A, is A, B, A. Now, if we were to start from B, right? Then we can obviously go to A and then go back to B. This is a double edge. This is a double sort of error that we were talking about. With a directed graph, if you were wanting to show that A can go to B and B can go to A, then you'd have two arrows. In an undirected graph, these wouldn't have any arrows at all, but you could still be able to go to A to B and B to A. That's what an undirected graph is defined as. So if we start from B, we can go to B, we can go to A, and we can go to B. So B, A, B is if we were to start from B. And then B can also go to C, which can only go to D, right? So if we were to go to B and then we go to, let me get my pointer up. If we go from B and then we go to C, then we go to D. We can't go back to C because that won't get us to B, and that's a repeat. If we go to E, it's a dead end. But if we go to B, then that's a completed cycle. So what we can do, that's another cycle right there. B, C, D, B, okay? And that is the only other cycle for if we were to start at B. Now, if we start at C, we'll go, obviously the only way it can go is to D. So we'll go to D and then we'll go back to C, that's CDC, that's another cycle. So we can go to C, we can go to C, can go to D, and D can go to B, and B can go to C, so that's another one. C, D, And this might seem like a lot of work, but that's just because I'm explaining it and explicitly going through all of it. As you like do a couple more sample problems, you'll get the gist of it, and you'll be able to do it a lot faster. Right, so C, D, B, C, like that. And so that's the only other possible cycle if we start to see if we don't want to look into any repeats or anything. So then we started D. D can go to E, but that's a dead end. D can go to C, and DCD is another one. Oh, it's getting really hard to write all these down. D, C, D. D can go to B, B can go to C, and B could D, and then C can go back to B. D, B, C, D, B, C, D, and D, B, D, and that's the only other cycle, I believe. If you guys think I've missed any, just let me know. So the answer should be on the next slide. So it's ABA, BCDB, and CDC. So it cleared all of them, but essentially what I did was list all of them. So now I'm going to talk about how there's certain repeats, right? So when I drew so obviously ABA was one of them, and that's because we went ABA, right? Now BAB, you're essentially drawing the same line, right? So if I were to clear that, even though you're starting from B and you're going back to B, you're still drawing the exact same line. You're drawing the same line, same sort of shape, right? And in the same way, we counted all the ones having to do with this triangle right here, BCDB. So that's the triangle right here. Now, if we were to do DBCD, for example, you're still going to be drawing that triangle, and because of that, they call that repeat cycle. So you don't want to. The question asks for different cycles and not all of the possible cycles. So if you like draw the same shape a second time, then that's a repeat cycle and you don't want to count that. So CDC would count as another one because it's a new shape in a different location, right? DCD would not be a different cycle because, it's the same line. You're just drawing the exact same line. So this is one cycle right here. This is a one cycle right here. This is another cycle with a triangle. And then this is the last cycle with C, D, and C. Does anyone have any questions before we move on to the next problem? Okay, I'm going to take that as enough. So we can move on to the next problem. So now we're going to be looking at finding the total number of different paths from vertex A to vertex C of length 2 or 4. So let's first draw the adjacency matrix for this. Bear with me. So this is going to be a 3 by 3 matrix, so there's 3 vertices. So this is how you'd set it up. You'd say A, B, C, A, B, C. So this adjacency matrix would be for length 1, right? So these are all the paths from length 1. So this would be the starting point, this would be the end point. So is it possible to go from A to A with one edge? And that is correct. Yes, it can. So what you do is you draw 1. You'd write a 1. So that means A can get to A with only one edge. It only needs one edge to get from A to A. Now if we go to A to B, there's no edge connecting A to B directly, so that's 0. There's no way to get from A to B in one edge. And A to C, there is an edge going from A to C, so we can write that. And when we fill this out, from B to A, there isn't any. From B to B, B can go to itself with the loop sort of thing. So we'll write a 1. B can go to C. Keep in mind C can't go to B because it's a directed graph, so I believe most of the graphs in ACSL are directed, so you shouldn't have to worry about it, but just know that just in case. C goes to A. C does not go to B, as we just mentioned. And C does not go to C, it does not go to itself. So this is the adjacency matrix. This would be a length 1. And so how we would find paths of length 2 or 4 is we would square this matrix using matrix multiplication. We would multiply this matrix by itself to get all paths of length 2, and we're looking for vertices A to from all the paths from vertex A to vertex C. So the next slide will show you the matrix multiplication right here. So it was 1, 0, 1. So this is the adjacency matrix right here. This is the original adjacency matrix. This is the matrix for all paths of length 2, and this is the matrix for all paths of length 4, right? So if you look from A to C, if you had an A here and the C over here, of length 2, there's only one path you can take to get from A to C of length 2, and there are 3 paths of length 4 right here. If you put an A here and a C here, then this number right here represents the number of paths you can take from A to C, and that's 3 different paths. So is there another question? Okay, so right here, this will give you, so if you're given the adjacency matrix, you're gonna have to draw the graph. So just keep in mind that that's A, that's B, that's C, oh wow, okay, that's C, that's D, same thing up here, that's A, that's B, that's C, and that's D. So when you're drawing the graph, just look through the matrix. You see, oh, there's no path from A to A. So if you draw A, then you know you don't have to draw a loop sort of arrow because it doesn't go back to itself. You'd have to draw an edge from A to B, and you'd have to draw an edge from A to D. So you draw the 3 vertices, A to B, A to D, and then for B, you draw a matrix arrow back. So if I were to draw A like this, and you can be, it's not exactly like, you can be pretty abstract with this sort of thing with the drawing. So A to B, right? So you can draw like that. That's how you draw an edge, A to B, and then D would also get one like that. And then B to A, you draw an arrow on the other side like this. You don't have to draw like another entire line, just draw an arrow on the other side. B to A, and then B also goes to D. Like that. And C goes to A, so we can just like sort of draw C in the middle. We could draw C in the middle. And then we can put C to A. Again, you can draw any, like the vertices where they want. You just have to make sure that everything's accurate. So C to A, that's the only one. And then D goes to B, back like this. And then D goes to C as well. So you just draw like that. So that's how you would draw the graph for this. It's obviously pretty messy, but that's the gist of how to draw it from the adjacency matrix. And this is a solution. These are 2 different valid drawings. Obviously, you can draw it however you want, however like you want to orient it. Doesn't really matter. And that's all we have for graph theory.